Hello, today I'm going to be talking about banded iron formations and their debate of origin. So first starting off, what is a banded iron formation? So banded iron formations, also known as BIFs, are repeated layers of iron oxides, which include magnetite and hematite, alternating with bands of silica-rich shales or cherts. These deposits are primarily found from the Precambrian era. Banded iron formations can be isochron age dated, with the majority of these formations occurring during the ages of 3.5 billion to 1.8 billion years ago. These ages can be related to different atmospheric conditions of the Earth. So, banded iron formations are extremely important to economic geology. This is because they are crucial to our economy due to their large economic impact of amount of iron deposits. China and Australia are the world's largest producers and both have enormous reserves of banded iron formations. Although we also find banded iron formations within North America and South America, as well as Europe and different African countries. So banded iron formations, despite extensive research, the mechanism of deposition is still unresolved. There's a debate between biological-sedimentary or submarine hydrothermal. Both of these viewpoints will be looked at in today's presentation. So looking at this picture, we can find that most of our banded iron formations are forming around this peak around 2.5 billion years ago and completely going extinct around 1.8, with a smaller amount popping up around 0.6 to 0.7 billion years ago. Now talking about oxygen in the early Earth. So first, the Great Oxidation Event. There was a rise in oxygen that occurred in the atmosphere from 2.4 to 2.1 billion years ago. This notion of the GOE, or Great Oxidation Event, is deeply entrenched within our understanding of the Earth, and with only a few researchers suggesting otherwise. So this concept is well understood, and we're going to be representing this as the true fact of this presentation. Although the controversy comes in the timing of the first emergence of the O2 producing photosynthesis. So as we can see in this um, diagram, we're finding we're having a bump in um, free oxygen, which then correlates with this oxygenic photosynthesis, which then begins in 2.4 billion years ago. Now, looking at our first argument or controversy on this topic, and that is looking at the submarine hydrothermal model. So looking at this model, iron formations are extensively studied over 100 years, but there still is a controversy. Firstly, seafloor hydrothermal events have been studied only since the late 1970s, but has shifted the focus to this origin. Geological constraints have challenged the assumption that the Fe formations were continuously deposited before the increase in atmospheric oxygen. Talking about mechanisms, and how did we have these large amount of increase of dissolved iron in marine reservoirs? There are three possibilities. Number one, in a reducing atmosphere, there could be one with a low oxidizing potential. This would allow for a lot of dissolved iron to be taken and put into these marine reservoirs. The second is a low marine sulfate or sulfide concentrations, thus allowing for more of this ferrous iron to be within the marine reservoirs. And finally, if we had a high hydrothermal flux of iron coming from different hydrothermal vents. So deposition. This is an important picture that we're going to be looking at for the depositional model of sedimentary banded iron formations. So within picture of the low sea level, we are finding that shelf sediments, a mixture of carbonates and volcaniclastics, as well as siliclastics, are resedimented to the basin floor. So they're going down this slope, down onto the basin floor and being deposited. This is due to the erosion of the shelf during the low sea level. This allows for the sediments to be pre-deposited on the bottom of the floor and these basin floor fans depending on the slope input as well as the shelf input and the erosion of the bedrocks. During high stand in this photo, high sea level, sediments are accumulating on the shelf and not going down into the basin floor. So therefore, the erosion of the bedrock and shelf sediments does not input towards this bottom section. Although during high amounts of the sea change and the changes in the sediment pattern, there could be volcanism occurring. This volcanism would allow for an increase in seafloor volcanism that would feed the different input from these iron-related underwater volcanism, which would then allow for the banded iron formation's iron input. So then, depending on when the sea is at a low sea level or high sea level, depends on when and the different inputs are being inputted. So for low sea level, we're doing our siliciclastics, and for high sea level, we're putting in our iron formation or that iron layer. So questions to consider: if redox states are major controls on iron transport and deposition, why were large banded iron formations at 2.45 billion years ago? Well, this is because there was one possible link could be the pauses in global tectonic activities. So this would be there would be a higher amount of iron input into the water, which would allow for more banded iron formations to form and less siliciclastics to be broken down on these shelf portions due to the lower amount of tectonic activities, which would allow for less shelf input, although higher amount of volcanic iron. Secondly, if the atmosphere of O2 rose in the early Paleoproterozoic, why or how is there a second peak in Fe formation depositions at 1.8 billion years ago? If it was a biological deposition, how could we have these atmospheric O2 in the early Proterozoic still depositing these banded iron formations? This second opening could be a possible link to a mantle plume event. So more iron being put into the system, the more mantle or underwater volcanism there is, the more free iron, and the more iron there is, the more and larger banded iron formations are being deposited. Finally, why are we having no Fe formations during 1.8 to 0.7 billion years ago, or until the end of the Neoproterozoic? This could be because there was no underwater volcanism due to the different snowball Earth uh, glaciation events that were occurring at the time. There was um, no volcanism to feed the iron needed to form these types of deposits. Trace elements. So rare earth elements are important and they're one of the best geochemical tools to understand the origin and the deposition of these Fe deposits. Some REE studies focused on EU anomalies and CE anomalies. The EU anomalies uh, could be used as tracers to trace the hydrothermal input, while the CE anomalies are used as redox proxies. Studies show that the Fe in banded iron formations have depleted REE patterns. This is the same signature that mid-ocean ridges and hotspot activity shows. Therefore, this could be the source of the iron. So these two diagrams are analyzing different trace elements. So this is the samarium neodymium ratio, and this is just the neodymium in the neodymium in each mesoband. So the top one is showing how the relationship between the total iron concentration and the neodymiums are dependent on each band. Therefore, each band is slightly different than the next. And secondly, we're finding that the total iron concentration in each band is different due to the neodymium, and this could be a result of different mixes of different inputs for each band. Therefore, using these trace element profiles, we find that iron and REEs are not fractionated during the spreading centers. So therefore, this pattern is something that we can trace back to it, back to those original volcanic events. While the large EU anomalies indicate the presence of hydrothermally derived iron. Another interpretation is that the dilution of these hydrothermal fluids, which carried the iron, would decrease in EU anomalies as the distance from the hydrothermal vent increases. And this has been proven by looking at these different trace element profiles. Another reason why these banded iron formations can be associated with the hydrothermal vents is their association with VMS deposits. So VMS deposits are large sulfide deposits which are mined for economic value, and these types of deposits are found around or similar to the times where there were mantle plumes and the time where there were banded iron formations. Although when we're looking at the mantle plumes over time, when compared to the banded iron formations over time, there are still small differences, but we can correlate the trend of these banded iron formations in later banded iron formations. Finally, looking at the GE over silica ratio, we can find that the Fe is related to high temperature hydrothermal vents, while the Si concentration is due to waters fed from the weathering products of the crustal landmass. So this is just by using this relationship and trying to refer it back to the original source. Alright, so that was the whole hydrothermal model. Now we're going to be looking at the other models, the competitor to the first one that we had just been talking about, and that's the biological or sedimentary model. The interactions between microorganisms and dissolved ferrous iron in the ancient oceans offer one possible means of mineral precipitation. So the first type is when we do have oxygen. We are having oxygen photosynthesis. So therefore, there must be some amount of oxygen in the atmosphere for this to occur. So what we'd do is we'd have a ferrous iron input from seawater volcanism, and then that would be feeding the water with this ferrous iron. Once that happens, once it is above the what is called the redox line or the redox line, there is a layer of oxygenic photosynthesis, which is taking the ferrous iron and is turning it into iron oxyhydroxides, which then would fall out of the water column and would fall onto the continental slope. So this oxidation is by chemolithoauthotropic species such as Galena ferruginea, and these are limited photosynthetic oxygen. Although there is also a way to explain that bacteria could oxidize the ferrous iron by the reduction of CO2. So this would be produced in an anoxic photosynthesis reaction. So therefore it does not require the oxygen like the previous slide. So in this equation, we are taking our ferrous, iron, and carbon dioxide and creating anoxygenic photosynthesis, which produces iron oxyhydroxides, which then deposit onto the continental shelf. So the biological and sedimentary model can be explained by using the different ages as well as the amount of free oxygen in the atmosphere. As previously, we looked at the oxygen over time figure, although in this slide we're going to also be looking at the isotope ratio figures. So we found that there is a summary of carbon and sulfur within the different profiles, and we can relate these when we're having the different banded iron formations. We're finding a lot of trace metal enrichment in marine sediments, as shown a significant oxidative weathering of pyrite and sulfide minerals before the GOE. So before the GOE, we're finding a ton of these banded iron formations. Although after the GOE, we're finding a disappearance of distinct non-mass dependent sulfur isotopes. So this is done by testing the sedimentary rocks after the 2.4, 2.3 billion years ago, and then we find this non-existence of this specific isotope. So that could be showing why we would have this big cutoff or big decrease after the GOE, is because we're losing those specific anoxygenic conditions and now going into a favored oxygenic position, where then different photosynthetic reactions can start occurring and not favoring the iron hydroxide synthesis. So the biological sedimentary model shows that most major BIFs have a depositional rate of 19 to 225 meters per million years. Although some BIFs can have rates up to 1,000 meters per million years. So therefore, we want to first determine if it is physically possible for both an anoxygenic and photosynthetic organism to produce these large of ferric and ferrous iron deposits. So using different conditions like free oxygen in the water, iron concentrations, and pH levels, we can determine how much moles of ferrous iron can be produced, or ferric iron can be produced per cell, and the density, and using a standard density of a microbial mat, we can find that there would 100% be an ability for these microbes to be produced over 100 meters per million years of these large mesobands. So therefore, it is mathematically proven that these biological cells could produce this much iron. So oxygen bacteria growing in the water could also produce up to 2 to 3 times more iron than those precipitated by banded iron formations, although this would be considered in the optimum conditions. So in the biological sedimentary model, we can look at the rare earth elements just the same as we did for the hydrothermal model to try to help prove this side of the debate. So therefore, we can see kind of two different trends. In the early Proterozoic, we're finding a positive CE anomaly, while in the late Paleoproterozoic, we're finding a true CE anomaly. So this is because the CE anomalies help prove redox reactions. Therefore, when we're having the higher amounts of oxygen, we're having a higher amount of redox proxies. The oxidation of the Ce3 is greatly reduced, including for Ce solubility, which is resulting in the preferential removal of the iron and manganese oxyhydroxides, organic material, and clay particles. So if bacteria was to produce these banded iron formations, we would also have to have sufficient trace minerals and other nutrients available in the depositional basin. If we measure these concentrations in recorded banded iron formations, we can find that we are having a much higher production of these different nutrients, including vanadium, than what would be needed in the actual varved mesoband. Therefore, we are having a higher amount than is needed. Therefore, it can be proven that there would have been enough nutrients in the water column to allow for these photosynthetic or anoxygenic reactions to occur. So why is there more trace metals found in the banded iron formations than the biological organisms? Because the Precambrian oceans, there would have been types of bacteria which would have required this nutritional support, and the metals and nutrients would have been buried and incorporated into the sediment if they were not have been used. So therefore, since they weren't used, they would have been buried at a higher rate. Finally, why is there more trace metals found within the banded iron formations than the biological organisms need? Because there could have been the actual availability could have been less than the measured due to the diminished amount from scavenging properties of the Fe-rich particles as they settle down to the bottom of the sediment, and the extent of precipitation would have subsequently be controlled by such factors as salinity, fluid composition, and pH. Conclusions for the biological sedimentary model. So the ferric iron oxidation has the possibility to produce the bulk, if not all, of the ferric iron in the banded iron formation. There is extremely complex roles played by other bacteria in the formation. A negative CE anomaly helps prove the redox reactions in the late Paleoproterozoic. There is also sufficient amount of trace minerals and nutrients which could have been available to these different bacteria which would have produced the ferric iron. And finally, the genesis of the silica-rich sequences indicated periods of relative hydrothermal quiescence. Therefore, if there had been hydrothermal quiescence, how would there have been enough ferrous iron produced by these hydrothermal vents to produce these banded iron formations? And if it was a hydrothermal vent, then how could there be continuous banded iron formations if volcanism has been proven to be a on and off activity dependent on the different tectonic activities? So therefore, due to the amount of consistency of these banded iron formations and the sizes of the mesobands, the hydrothermal fluid deposition would not make sense in comparison to the biological sedimentary model. Finally, the last option that I will be looking at is the UV photooxidation of ferrous iron. So it is seen that the alternative for a biological model could be that there could have been a photooxidation of a high flux from ultraviolet photons coming through the Earth's atmosphere, which could have allowed for the rise of atmospheric oxygen prior to the development of the protective ozone layer. So this could have only happened due to there not being the protective ozone layer on the Earth, which then would have allowed for these high flux ultraviolet photons to be able to reach the area where it would have this reaction. So in this reaction, it is taking ferrous iron with a photon and turning it into ferric iron and hydrogen. Alright, thank you for listening to my presentation. Here are some of the references that I used for both the biological sedimentary model and the submarine hydrothermal model. Thanks.